tellurium-7. We are working on this. I want to share some background of this compound. Initially, in 2014, copper 5 tin to selenium-7 was reported, and they solved the structure from readable refinement from synchrotron data. And they suggested the space group is C2, and this is the cell parameter. So the structure is interesting because the structure is similar to the gene blend type structure, where this is anionic layer and this is the ordered cationic layer between copper and tin. And most interesting thing is that there is a dimer present in this structure, which is the tin to selenium-7 dimer along the C-axis of the unit cell. And they said that this dimer actually behaving as a channel of this copper ion motions or something. So that is why this compound shows metal-like electrical conductivity. Then after that, they have taken the DSC and PGA data, and you can see that this DTA and PGA data, there is no phase transition, or there is no signature of phase transition is present. As well as they have taken the powder data at two different temperature, and also there is no trace of phase transition is observed. Then after 2014, 2016, and 2021, these two telluride and sulfide derivative of this compound also reported. So the main thing is that this compound is mixed valent. So if we have a mixed valent system, then we can suggest the charge balance by these two way. One is the we considering whole, and another is we can consider in copper 2 plus ion present here. So people suggested this fast charge balance system where whole is present, and that is why they said that the metal-like electrical conductivity is present here. And this copper 2 plus is not possible in the copper-based chalcogenide system, which is very rare in some cases. Also, the copper 5 tin to tellurium-7, which was not test pure, and also copper telluride and tellurium is present as impurity phases. But interestingly, there is no germanium-based system is present still now. So we have attempted to synthesize the as copper 5 germanium to tellurium-7. I have also tried with the selenide also, but the selenium compound is not possible. I tried several times. Maybe because of copper, germanium, selenium, their atomic radii is very similar. And also the tellurium has greater ionic radii. Also, its electrical conductivity is very low compared to selenium and sulfur. That is why this cationic ordering is taking place. That is why we have this copper 5 germanium to tellurium-7, not the selenide or sulfide. And similarly, there is dimer is present, and the compound consists of several type of distortions. Like there is some bond lengths are already distorted, angles are already distorted. So we can explain the structure by using Pauli's second rule, which says that if you have some different type of charge balance system, then the anions will try to compensate its charge by compensate the strength of the bonds. So that is how we can explain the structure in our system, and that is why the compound crystallizes with the C2 space group, not other space groups of the monoclinic system. Now, then I try to synthesize the compound in bulk phase in our lab by using the same temperature. But unfortunately, we have copper telluride and tellurium as impurity phases, as well as one unidentified phase is also present, which I do not know what is. And then I tried to do the annealing and Cohen's method at various temperature. Also, the same result is coming that copper telluride and tellurium is there. So then I found one literature from Kanak's group. They say they actually performed in situ powder excited measurement on lithium, copper 3, titanium, tellurium 4. And then they show that, and they use this temperature program, and at various temperature, they collected the powder excited data. And they show that at high temperature, this lithium, copper 3, titanium, tellurium 4 is forming. But when the temperature is cooling down, that time copper telluride and tellurium is forming. So it is not present at the high temperature, but when it's cooled down from the high temperature, then they are forming. So then click a reaction mechanism that if we can heat the sample very rapidly, if we synthesize the sample at a very short time period, and if we cool the sample, very rapidly, then this copper telluride and telluride cannot form. So that is why I contacted the Jointo and
I have
he successfully synthesized the sample. And
a
it is
question here
actually,
on the previous line.
yeah.
Is it known why the copper telluride and tellurium precipitate out when you do slow cooling? Is that understood?
So when it is cooled down in 4 hours or 5 hours, then they are actually forming
Mhm.
copper telluride and telluride.
So I think I will just add Kedar because that is what is sort of the common phenomena in many systems. Actually, if you allow it to cool down slowly, then
Yeah.
that this is the binary.
Phases
It's
are.
a very stable compound. Actually, it forms along with the main phase.
Mhm.
Yeah, and also at 450 degrees centigrade, there is a eutectic point is present of copper telluride. So
Mhm.
that is also a chance of forming a copper telluride at near to the 450 degrees centigrade temperature.
Mhm. Okay.
And also, we do not know when we heat the sample at high temperature in many tellurides. I have several examples that in copper-based telluride, we always have this copper telluride and tellurium at a minor percent as well.
Yes.
It is always there when we
Yeah.
have slow cooling or quenching or any other way. It is always there.
Yeah, we have it in Jayanta's copper and titanium telluride as well.
Yeah, but he will show you something today.
Okay.
He has some success.
Hmm.
Okay, and yeah, then I'm going forward. Then, so this is the phase pure. But okay, one question is that Jointo told me that one of your postdoc actually he suggested that maybe the copper telluride is present in the sample. That is why we have a shift in the powder data.
Mhm.
So this is the old into data which Jointo showed initially, which has very high shift.
Mhm.
But the same sample he actually sent me here. This
Okay.
is the our data in our instrument, and also Jointo has taken another data at the NTU. There is less 50
Okay.
with the same sample. So that is why this shifting is coming from the instrument because he has pressed a lot
Mhm.
when he was collecting the data in Bragg-Bento geometry.
Mhm.
Maybe that is why it is instrumental error is coming,
Yeah.
not coming from the sample.
Mhm. Yeah. I mean, that's
And
expected.
and then this is our I have collected the long PX30 data and we achieve around 1 lakh of intensity and this is a readable requirement. So it shows more or less test pure,
Mm.
99% at least.
Yeah. It's amazing. I mean, that's incredible. I mean, we haven't even the rapid joule heating, the cooling is okay. It's of course fast, but if you really want to make it even faster, there are tricks we can use to do that too, right? So, one way is after synthesis, we can drop it in liquid nitrogen, or like just use a high powered fan. We haven't even tried those, but even with this room temperature cooling, it looks like the cooling rate is fast enough to not allow the copper telluride precipitation, right?
Yep.
Oh, this is a great success actually, yeah,
Mhm.
of your Joule heating technique. Actually.
Mhm.
Yeah, also it's shortened the time period. Like days of heating, it's come to the minutes.
Yeah,
After 2 minutes, we have the physical sample.
yeah, that's amazing.
And the structure is not distorted actually, even though it's a very fast cooling, but it
Right.
yeah, it forms the structure we have
Mhm.
seen in our single crystal X-ray data. Yeah.
Yeah, it's amazing. But this is great. I mean, if you think about it, but if you, yeah, I think it's a really good result. It's not single crystal, of course, but it's probably very large signal, very large grain.
It's great. It's great. Yeah.
Yeah. Then joint actually perform the phase formation mechanism. So he took the ball milling sample and at various temperature he heat the sample and then ultra quench the sample and then he is taken the data.
So I think
So
this is a
as
slightly different way of doing things. One of them is our bulk synthesis, right? So the previous result, Jayanta, was that on the DJS? Or, yeah, Kabutaba. Yeah. This is a different way of doing it. Still rapid joule heating, But DJS is something we came up with. Cover thermal is where you actually put a carbon paper, maybe Jayanta told you already, but you put a carbon paper, you put powder, and then you annihilate, and then you can stop the reaction at many points because we can actually to stop the reaction at various temperatures. So this way you can actually map it out quite nicely. So the temperature on the y-axis here is the temperature to stop the reaction. Is that right? Yeah. So you could basically do, and that reaction is also very fast. If so, yeah, 30 seconds. And so you can actually collect all of this data within one afternoon. And the XRD was done here, or was it sent back to ID Kharagpur?
Yes, still some shifting is present here,
Hmm.
but this is also coming from the instrument.
So there are some additional peaks in the middle, right, between 32 and 40 and stuff. What are the? And I see the tellurium peaks, but there's a few more that you have
This
not.
one,
Yeah, that one at high temperature, then at low temperature, there seems to be some between 32
I
and
will characterize, but these peaks are coming from the phase copper 5 diamond aluminum
okay,
7.
okay,
But I will investigate on more on this part,
yeah,
this region, if we
okay,
have any interesting phase as well.
yeah.
Yeah. But here we can see also that little phase of copper telluride still present.
Hmm. I was going to
Very
ask,
weak.
what about the copper telluriums? There is some because when you, I guess this is different from what you would do, right? Because you go to your reaction temperature and you cool down, and when you cool down, you start to form the copper telluride. But here, what you do is that you go to, let's say, 600 degree Kelvin, 600 Kelvin, and then that's very fast and it cools off. So there should actually be no copper telluride in any of the cylinders. So maybe it's just some minority copper telluride somewhere, not otherwise.
There must be some copper telluride.
Reaction. Hmm. Nice. Yeah, it's very fast. Because the powder cools even faster than the bulk. Because when you put the powder, it's actually in contact with it. This is in contact, right? You're not doing radiative cooling part. This is directly dropped on the carbon paper and annealed. Is that right, Jayanta? So it's in contact. So the fastest, so this method has been used to do nanoparticle synthesis. That's the fastest. We can imagine the surface to volume ratio is much higher, and so the cooling is super fast, like 10 to the power 5 Kelvin per second. This is what people have reported for like high entropy alloys, etc. But here it's not really a nanoparticle, right? It's micron size particle. So the cooling rate is not so fast, but still much faster than the bulk that you saw on the previous slide. Yeah.
Okay.
Yeah. So quite good, I think. That's quite consistent.
Yeah, it's really yeah. So I mean, ternary phase is I mean, sort of that we can conclude like the ternary phase is the kinetical control on, and then copper telluride is the
Yeah.
thermodynamic control.
That's exactly right.
Yes.
Yeah. So, I mean, I think it's successful, right? There's no doubt about whether it's successful or not. Whether you want to do more, I mean, is the XRD from 99% phase purity, is that good enough to report a new phase? Or
Yeah.
do you need to do more things like beamline or single crystal XRD? Not required.
No, not at all, because we already have the model from
Okay.
single crystal XID, and we have checked the data we have got, and
Mhm.
and we did the detailed refinement.
Yeah.
So we have checked the atom fit as well. So it's perfect
Amazing.
with a residual factor of 5%, 6%. So it's really great actually. Yeah.
That's really exciting.
Yeah.
Okay.
Okay, so shall we move forward?
Mhm.
Okay. And then we have taken the EDS color mapping. If there is some other variation in the mapping, but we can see this is clearly
Yeah.
okay.
Yeah.
That there is no case of any binaries or other things.
This is done in NTU, right?
This is done in India.
This is in the newer SCM, not the old one, right? Jayant? Yeah. Yeah.
Okay, now this is the thermal analysis. Um, the phase decomposition started from here,
Mhm.
but before that, we have some interesting point at close to 350 degrees centigrade or 621 Kelvin. So this is the DSC plot and this is the heat capacity plot. So there is something
Mhm.
happening in this temperature. And same thing actually happening in the transport property measurement as well.
So Kedar,
But after,
yeah, just one point I will add that Kedar, after looking at the DSC data,
Yeah.
so what we have planned that we will go for temperature variable single crystal XRD measurement. Then we could be able to see that what is actually happening.
Okay.
Uh, I mean above this particular temperature where the peak is shown actually.
Mhm.
So that we will do it in future actually to
Right.
look at the change in the if there is any change phase transition actually in the structural phase transition. Yeah.
Right. But the small peak, I'm not an expert at this, but the small peaks should not be a phase transition, right? Usually we have a very large peak in enthalpy. Is
You,
that
you
correct?
yeah, you might be right because maybe there is some
Small phases.
just local distortion or like that. But yeah,
Okay.
because but to make sure that we will just check that we will collect the diffraction data above this 600 or
Okay.
15 degrees Celsius. Yeah, a
And
single.
what's the origin of the peak at 777?
Uh,
this is decomposition of the phase. So
Okay.
yeah.
So basically, it's if you were to freeze this, you take the sample from and put it room temperature to the XRD, you'll get mostly copper telluride and tellurium and other binary phases. Is that what we?
no. The
Mhm.
phase is when we cooling down, the phase is actually forming with additional binaries.
Okay.
Phase is again forming.
Okay. It's really
After
actually
taking the DSA, join to send me the sample. I
okay.
have taken the data here.
Mm.
The phase is again forming with including some binaries.
Okay. That's cool. It might be good to do the TEM on those actually for the paper, you know. Like you take a sample as made, and then you go through the DSC cycle, and then you take the one with the precipitates forming. If the majority phase is still that, and we also measure the transport properties of those, because it depends on how the precipitates form. The CBAC, I briefly noted, the CBAC was positive, right? In the next slide. Yeah, so it's like P-type metallic. So I don't know the band structure. Maybe we need to discuss the band structure and stuff. But it's possible that if the right kind of precipitates form, then you get de-doping. You might increase the CVAC coefficient. And the conductivity is already very good, right? This is like C1 per centimeter, like at room temperature, it's 6,000 C1 per centimeter, right? It's a very good number. So even if you drop it by an order of magnitude and the CVAC goes up, that's also very promising. But it depends on what precipitates form, right? It needs to be an N type. So de-doping precipitate that form. So I don't know if copper telluride is N type or not. Do you guys remember? I'm not sure.
Check once. Yeah.
Yeah.
Yes.
Yeah. This part we will check once and
Yeah.
then.
Also, whatever things is happening in this temperature, this is again it's March at the
Yeah.
high temperature as well.
Mhm.
And the cycle is repeating again and again, but there is no signature in thermal conductivity.
Interesting. Yeah. Thermal conductivity is not super low.
Yeah, but it is actually low compared to the tin based compound.
Okay.
Yeah.
So I mean,
It's because
solving the
tin based
structure,
compound is higher.
solving the structure would be good, but if you get some more insight from the band structure and also to the phonons. So since the structure is solved, one thing we can do for sure over here is we have a automated code to study thermal conductivity, intrinsic thermal conductivity of the material. So we will run that code. So what it basically does is DFPT, density functional perturbation theory. So it does an elastic relaxation of the unit cell. Okay, so it's only in the elastic limit. All right, it's not a. So there'll be some harmonicity, but in the small displacement limit. And you can look at 4-on-4 interactions. It's called auto kappa. We have the code for it already, and it's basically runs on a supercomputer. So it's already automated, and the analysis is quite relatively straightforward. So we can actually do that. I mean, it take a couple of weeks to run it, uh, but I think Jayanta just give the structure to Nongwei, and he can help you run this calculation. I already spoke with him yesterday. You can talk to Andy first, and once the band structure is done, then we can actually go for proper 4-on calculation as well.
Yeah, Kedar, we have preliminary band structure calculation as well. So
Okay.
probably we can just
Okay. If you have like the postcard file or stuff, that VASP file would be useful. So whatever structure file you have, SIF file and the postcard files,
yeah.
if you send that over, that'll be a good starting point. Then we can just get that as an input and we can do the autocopy. We might do some additional relaxation. The one thing we typically do is we just make sure it's properly relaxed, symmetry constrained, all that stuff. We have some tricks to do that, but we'll make sure that's done and then we calculate the thermal conductivity. So we can look at the full dispersion.
Okay.
And you said the complementary phase that has high thermal conductivity is the copper germanium cylinder, which has the higher thermal conductivity. Or you mentioned that.
No, copper tin, copper tin chalcogenides. There is no report from copper germanium
Okay, I see.
chalcogenides.
Any calculation. So this is the only one that you
This
can
is the
stabilize because of the ionic radii. Right. So the copper tin telluride, have people looked at the thermal transport? Is
yes,
that
yes,
okay?
yes.
So please send that paper over. We will take a look at it, and then we'll
Okay, okay, okay,
see
okay.
what we could do
Because
is
I have already added the citation, then I
okay.
sent it.
Yeah, yeah.
It's also set.
So Jayanta, just look at the that material and see what is the origin in that paper for higher thermal conductivity and what happens to the germanium. And we can have a hypothesis and then we can look at the scattering times and then make a nice story out of it.
And also the this is the total thermal conductivity. So lattice thermal conductivity might be very low
Oh, that's true because
because we have very high electric
I forgot
conductivity.
about that. Yeah, sorry, my light turned off. Yeah, actually, like the for this high conductivity, I mean, but not much probably. Like it's 200, 300 cm per centimeter. I don't know, maybe between 0.1 and 1 somewhere is my guess.
Yeah, but from
So
band,
we,
as far I remember that Ornov, it's a metallic, right? There is no band gap. Yeah, it's just
Okay, the band structure is metallic.
yeah, yeah.
you can just show if you have it right now, actually,
Okay, so it's metallic,
because it may not be very
right?
useful for thermoelectric applications. Because, but
Yeah,
I think this,
metallic. Yeah,
yeah,
yeah then there's no point trying to.
yeah, that is why you just
Oh, it's already
yeah,
metallic.
it's just metallic
Yeah,
actually.
it's quite definitely in the band. What level of DFT is this? Is it PV Sol? What's the functional?
This is actually collaboration person.
I mean, Kedar, what is the question? Maybe I missed it
Is
actually.
it PBE level
I
DFT?
think PB,
level.
GGA, PB calculations. Yeah.
Those are not super accurate, but I don't think you have a lot of. There's like nothing magnetic or anything here, right? So it should be pretty. There's no correlated electrons. Maybe that's good enough already.
But also I mean, also the experimental result will also show this metallic in
Yeah,
nature.
so it's
There are been,
consistent.
yeah, yeah.
Yeah, so I mean, anyway, you can send us the cell. We will just do the photon calculation, and then we can compare.
Yeah.
So
Yeah.
very nice. Again,
Now,
there's a little spoiler.
I will the main USP of this. I mean, this is a new compound, and you could be able to prepare phase pure sample by Joule heating technique. That is really great, actually.
Yeah, that's pretty
Yeah.
amazing. Actually, we've been trying this space pure for a while. This is the we tried silver antimony telluride initially with its pure phase. I mean, that's also eutectic compound.
Okay.
But we know it's eutectic. I think it's like slightly silver poor, and I forgot the exact phase diagram, right? But we didn't succeed. Okay. Then we tried some other materials too, and this is relative success. I mean, like the copper titanium telluride story.
Yeah, yeah. I mean, I mean that works, no? So just few more tricks and that works. Yeah.
Yeah, maybe I don't know the new tricks. I remember the last one was 85% phase purity.
Yeah,
So
but now 99%. That's why the
is that right? Okay, wow. What is the trick? I mean, this is a new.
I think Janta will tell you.
Okay, you don't want to steal his thunder. Huh? Okay, this is very cool.
Yeah.
Okay. Okay. Then I need to take the XPS data from your facility because I have taken the XPS data from our facility,
Yeah,
but it shows the germanium is present in class 2 oxidation state.
yeah.
The
You
germanium level
mentioned
is
this to me
13.
a long
I
time.
don't believe that germanium is present in class 2. It must be present in class 4 oxidation state.
Yeah. So we will
Other
run.
results are okay.
Yeah, our XPS is the N1 and N2 that we have access to is down for a while now. But in another institute here where I work, there's Jayanta, you can give the sample. Ask Pepe, he knows who to contact. And you can just pass the samples, tell them we're working towards the paper. Pepe knows how to handle it, and we should be able to get data for you in a few weeks. I don't think it'll be a problem.
Because this is important as the compound shows magnetism I had.
Hmm.
So then this study might be very important.
Yeah. And I think this question also, right? If it's the whole stabilized or copper 2 plus stabilized, this will help in that as well, right? So,
Mm. Okay, so this is low temperature transfer measurement is going on here, negative measurement, and
cool.
we need to check variable temperature PXA XOR if there is some transition.
Nice.
And as heat capacity measurement, I require because if shows ultra low thermal, lattice thermal conductivity is very low, then we can check with heat capacity measurement as well.
Yeah, we should do that for sure. So you can use the Dulong Petit limit, and it's usually pretty good, but actually it's better to do a real measurement, right? Because you're assuming certain things in Dulong Petit. It's high. You need to do that. You can. Okay, then you can do it in the PPMS. We don't have the we don't have the TTO. We have the TTO, but we don't have the thermal estimate.
But Arnav, just a quick question that why do you need the low temperature heat capacity? Because this doesn't show very low thermal conductivity, right?
No, thermal conductivity is not low because electrical contribution is very high, but it might show ultra low or low lattice thermal conductivity. Because if we eliminate the electrical contribution, then lattice thermal conductivity might be very low.
Well,
And
let's
that might coming because of distortion we see in the structure.
let me
Okay.
see
Okay.
So
number
we can see the Einstein mode or something.
But
Then we can explain it.
are you
2.4.
sure? Yeah. Okay. Yeah. So
Conductivity at room temperature is about 8, 8.
Yeah, you have sent me data, but
so if you have
it
electrical data, you can-
Yeah, 5.86. I just calculated it. Because L is like 2.4 10 to the power minus 8, and this is about 8,000 Siemens per centimeter. So,
get some,
yeah, this is
yeah,
a,
from here you can calculate the lattice contributions, and then you can check that whether you really need the CP data set
you're
or not.
right. It's ultra low. It's 8 minus 5.85 at room temperature. So it's about sorry 2.1 at room temperature. Lattice connectivity is 2.1. That's actually very
Yeah.
low.
Maybe Arnav you check once. Yeah. Once and then.
actually join to calculate the one thing, and we have also, but
Yeah.
it shows that the high temperature is becoming negative, lattice thermal conductivity. That is why I did not put the graph here.
Uh,
At high temperature, it is coming negative, lattice thermal conductivity.
Okay, you made sure that you took the T value at high temperatures, right? Because the formula is, K L sigma T, it's Ke. The temperature also needs to change. We already accounted for that, right?
Yes, sir. Which the coefficient we have already accounted, but after 500 Kelvin, it's becoming negative.
Doesn't matter. It doesn't matter. So you talk to Pawan, okay, Jayanta. He has a full Boltzmann transport calculation suite. We already developed it, and you can basically look at the conductivity in it because this is degenerate in the metallic limit.
Yeah.
It's actually relatively straightforward. So he has the code. If you just give him the data, he should be able to back calculate the K phonon, and then he can think a little bit deeper about it. So Pawan should be the right person to talk to.
Yeah. Oh, okay. Maybe he should be consulted actually for
Yeah. That's the
this.
code. I mean, this is a.
Yeah.
But if it indeed, so one thing to check also is that there will be an amorphous limit, right? Which is a simple calculation. So do you know what is the amorphous limit for this material, thermal conductivity?
Yeah, where the thermal conductivity become fade or there is no
Basically,
change. Stuff
if
like
there's
that.
no crystal structure, you just take the atoms together. What does it look?
Yeah.
And then you can calculate. There's a simple formula for it based on the specific heat. So you just take that amorphous limit, calculate it. You should be usually it's pretty small, like 0.2 to 0.5, something like this. It's very hard to go below the amorphous limit. So something else is going on then. The Lorentz number is changing. There's some interesting stuff in the system, physics based, right? Because it's unlikely that your total thermal conductivity goes. Um, so that means that Lorentz formula is not correct. You see, the conductivity
Mm,
is measured, temperature is observed. The only variable left is the Lorentz number. So if
mm,
your L sigma T is somehow giving you values that are too high than what is observed, then something weird is going on, right? That value must be actually smaller than we expect. That means the Lorentz number must be smaller than we expect, and it could be coming from this dimer effect or something. And that's fascinating.
Yeah.
That's not a trivial thing. Sometimes you need to find the origin of what is Lorentz. There's not many reports on this, and typically they need to be correlated electrons. And yeah, it's not simple. You can't just separate the K phonon, K electron in that case. So it gets complicated. But yeah, let's dig deeper. Let's try to plot it. Let's try to plot it first. Make sure you run it with Pawan, and then we can discuss a little bit more later.
Yeah.
Fascinating.
Okay. Yeah. So I think yeah. So I think this we should.
Mhm.
Janto, I mean, you talk as Kedar said here.
Yeah, talk to Pawan.
okay, so then this is done with this project. Then I want to discuss another compound,
Mhm.
which we recently I have solved the structure of copper, zirconia, selenium, these systems.
1, 3. Mm-hmm.
And actually, initially I was trying to synthesize the copper for zirconia, selenium for, but I have found the structure from that load, but copper for zirconia, selenium for is not found. And this compound has the similar structure with the bismuth tellurium compound.
Mm-hmm.
And we have here in bismuth telluride, we have the van der Waals gap between the tellurium atom,
Yeah,
but here the van der Waals gaps is present between the copper atom.
between the copper
And
atom. Okay.
yeah, in between copper. Yeah.
Interesting.
And also we have the vacancy in zirconia side as well as copper side. And this is the position, like the bismuth side is replaced by selenium here. And this is the copper side tellurium, and this is the tellurium is zirconium.
Okay, I see. So it's not just I mean, my first impression was that you have the A side cation, which is bismuth, and then that's partially occupied by copper
Mm,
and zirconium. But it's not
no,
that.
not like. And also I checked with bismuth telluride, all the structures like present in the database, but this type of structure with transition metal-based system is not there.
Mm.
Because initially there the antimony is present at the bismuth side or tin is present at the bismuth side, but
Yeah.
this is the interesting thing is that the copper in between the copper van der Waals gap is present, and also this is the structure is coming.
Well, is it because of the ionic radii or something? What's going on? Like, is it similar to, you said the copper was similar to selenium, right? In the last study as well. Is it true for
Yeah,
zircon?
it's very close to selenium. Maybe the copper channel is present. I do not know. I have to investigate more into the structure. I have recently just found this compound.
But the zirconium, what's the possible oxidation states for that? Can it also be negative?
Plus four.
Only plus.
Titanium, zirconium, it must be plus four.
Okay. The copper is going in the tellurium 2 side. Sorry, I'm trying to read your two tables. You have the copper, zinc, selenium. So can you explain the table once again to me? Which the copper one is going to,
This is the comparison. Bismuth is copper is going to fixed position where the tellurium 2 is present. I mean this one.
interesting. Wow. And the selenium is
And
going in the bismuth position. So the anion is
selenium is going to the bismuth position.
So this is Kedar just for comparison,
okay.
but this they are same structure type actually. So
And
but
same
again,
cell
that
parameter.
is only one crystals we have solved because Arnav is resynthesizing the sample.
Okay.
So we will once again have a look and then
Okay.
yeah. So just he wanted to show you that this is also another compound he found which is structurally related to the bismuth telluride actually, which is
Amazing.
very well known compound among the thermoelectric communities.
Yeah, yeah. I mean, bismuth antimetallic is the one prototypical material for all low temperature stuff. It's
Yeah.
basically layered, but the layering doesn't matter. It's very low band gap, and that's what makes it very good for room temperature thermoelectrics.
Yeah.
So, that's quite an interesting system. And the thermal conductivity is low. For the structure type, maybe you get low thermal conductivity. I don't know. Okay. It's hard to
Yeah.
predict.
We are in a very preliminary stage
Yeah.
work actually.
This is the structure explanation.
Amazing.
The way the layers are present.
This material has not been made before either. Yeah, the first time has been synthesized.
Yes.
Yes.
Yes. Yes. It's not neither material nor structures actually.
I see. And this is not through the rapid Joule heating method anymore.
No. 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 This is just
Locals.
programmable.
Mhm.
I mean, we have used programmable furnace
Okay. Got it.
for growing crystals actually. Yeah.
Sure.
Because without crystals, we are blind a little bit.
Hmm.
Yeah.
Nice.
Especially for the new structure actually. If we don't have any three-dimensional data, it's very difficult to
Right.
solve the structure from powder.
Yeah, that's right. So the way to do it perhaps is if you already have the structure from single crystal, then
Yes.
you can solve the powder and say yeah, it matches what
Yes.
it is.
Yes. 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 Yeah. Actually, that is what we have done for the compound Janto
Yes, yes, of
has
course.
purified.
I understand. Yeah. The of course what we want to do is to get the structure predicted through these machine learning models. You know, but I think it's still quite far off. We don't know which is stable and which is not. And I haven't read your paper, actually, someone on my to-do list, but I have seen the paper that you
All
guys
right. Yeah.
you don't. But I will look at it later more carefully.
Yeah. So probably, I think you know that your student is also my student. They just couple up.
Huh?
Yeah. So they are just
Yeah,
discussing about the machine learning work as well
like, yeah.
for metastable phase. Yeah.
Yeah. Hyman, I had a chat with him, I think,
Yeah.
because one of the problems we originally tried to solve with it are, if you think about it, it was like, hey, we should be able to stabilize any high temperature phase if you kinetically freeze it, right? So in thermoelectrics, one of the more famous compounds is germanium telluride.
Mm.
And I think it's cubic or I forgot rhombohedral at high temperature. And it's like I forgot that there's a low temperature phase, which is less symmetry. And so basically, we thought, oh, if we just go to the temperature, we know the cubic phase exists and kinetically freeze it, we should be able to lock the high temperature, high performance phase at room temperature. But we couldn't do it, after many, many attempts. And we don't know the reason why. This is where the whole metastability argument started. So I think it's nice that you guys are chatting.
No, probably I'm also very, I mean, confident that your Joule heating method could be capture a lot of metastable phases, which are probably, I mean, indicated in many papers, but not yet investigated in
Yeah.
details.
So I think what's fascinating is that what is the design principle, right? How do you choose which material you want to try, right? Because there's so many high temperature phases. What is
Yeah,
the principle to choosing? And if you know this guy also, the guy in Santa Barbara, uh, and Tony Cheatham's Ram Shishadri. You know Ram, right?
yeah, 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 yeah.
I met Ram at the JNCSR winter meeting last year,
Okay, okay, yeah,
and he was saying he had some ideas. Maybe he's like saying, if you have very small distortions in some of the atoms,
okay,
then energetically there's no barrier, kinetically there's no barrier for you to change the phase, right? And what Hyvon was doing independently was looking at volume change. If the volume change is very large, it's 3D,
yeah,
then the
yeah.
volume change is large means that there might be some kinetic barrier that you have to cross. And those might be easier to stabilize the high temperature phase. But I don't think the results are fully conclusive yet. I think that's where the discussion started. So, what could be the design principle amongst the database that exists that means that we have a good chance of stabilizing the metastable phase? And then we can try to do DJS on that. And that's sort of the idea.
Okay, yeah,
Yeah. So, any ideas you have on that, like more than welcome to chat.
yeah, yeah, yeah. Sure. We'll share.
Okay. This is quite nice. All right.
Yeah, I think that now the probably Jayant will tell the success story of telluride
All
compounds that
right.
we could be able to make it. So
Yeah.
today all success stories.
Amazing. This is the best meeting ever. Amazing. All right.
So, sir, I have a question that the Joule technique is so excellent, but
So
the
you have a
people,
lot of
why people are
background.
not using? Still, the why Joule
Jayanta, you have a lot
technique
of
still people
background.
are not using?
One second. Jayanta, you have a lot of background. Can you move somewhere else? Or ask the guys in the group to keep quiet for a bit. What's your question, Hornab?
My question is that Joule is it's an old technique. It's 19th century's technique, but why people still are not using recently?
So, I mean, it's a good question, right? So, you can check these flash Joule heating based techniques. It came from James Tour's group. I think he's in Rice University or something. So, they used it for like graphene synthesis. And so somehow that's one group of people. And then the other one was Julian Bing's group. They are the ones who invented this rapid. I mean, rediscovered it. And they were looking at some ceramics and looking at high entropy alloys. But somehow people didn't think about solid state synthesis for it, right? And I will tell you where our inspiration came was we looked at Julian Bing's paper and we said we want to do material by design and we want rapid ways of synthesizing stuff. So we end up trying all these different variations. I'm not sure. I think you're right. Like things like even induction heating has been around for the longest time. If you think about the principle of this rapid Joule heating, the Joule heat is going through the powder, okay, which I think in my, I don't know, okay, this is a heuristic opinion, right? Is that the atoms, like especially copper and stuff, they have high ionic migration. So, when you put current Joule heat through it, they will migrate under a field that gives you good mixing and that allows you to somehow form these beautiful phases. We haven't tried it, but induction heating, there's no contact, right? You can still go up in temperature and cool down very fast, right? So maybe that technique is complementary to this. We just haven't tried it yet. But yeah, the main idea is that you can heat up to the melt or close to the melt very fast and then cool very fast. So I think it was a bit surprising. But forming these bulk materials, right? The one that Jayanta is using, we have a spring. This is something we invented, right? Cheng Guang invented this idea. This doesn't exist. So like you basically put it in the tube, and then it's under compression already. Okay. So and then when it goes to melt, it compresses further. We haven't measured the pressure, but that causes it to be fully dense. I think that's the beauty of the synthesis. So there's some engineering tricks maybe that people did not use. But then that being said, you saw the powder-based synthesis that Jayanta showed. Even that is giving you pure phase. So it has nothing to do with compaction and everything. It's just something to do with rapid heating and rapid cooling. So yeah, I think it's unexplored. I don't know why people didn't try it before us. I mean, Jayanta is coming in next week there, man. He can bring a setup and set it up for you. No problem, man. We're happy to. The more people use it, the better, right?
Yeah, 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 absolutely, yeah. But
And
maybe Kedar, if you are okay, then I think I mean maybe Janta will first show this, and
Yeah.
then probably he can just come for a week when he will visit
Yeah.
his home, and then he can just little bit work on the single crystals. So I mean,
Absolutely.
yeah.
Absolutely.
So, but it's up to you that if you give him permission, yeah, to come.
Of course. Of course.
Yeah,
I
yeah.
mean, I gave him permission to go for holiday, so this is like a bonus.
In addition to holiday, at least he should keep 1 week for work.
Yeah. So I mean, it's up to Jayata. I gave him permission for holiday already. So if he wants to do work there, that no problem. I have no issues with that. Yeah. Mm. Mm. I see. I see. Amazing. Such a beautiful trick. The simplicity of it. Basically, I think the hypothesis was that you're doing it because there's excess copper telluride. That means that there must not be enough titanium to react, and we added more. I see. Beautiful. Man, that's fantastic. This is really amazing.
Yeah. Yeah, so actually, yeah, here I will add one sentence
Mhm.
that that is why Kedar, I probably propose the one experiment that
Yeah.
which probably Jayanta can do if when he will come for vacation. So he can bring the samples what he has prepared,
Yeah.
or he can just post it, and then we can uh, we can just grow a single crystal out of that powder. And if we
Perfect.
can do that, then probably we can check the diffraction pattern, because sometimes what happens in powder you could not see the superstructure reflection, which is very weak at room temperature. But if you take the single crystal data, you can just, because we have seen that for this compound,
I see.
so that superstructure reflection is so weak,
Mm.
probably it's very difficult to capture. I mean, when we integrated the data, even with the single crystal study.
I see.
So I think
Yeah.
that experiment he can just,
Sounds very
yeah,
interesting.
then he can just easily prove that it's a cubic phase, or just there are some superstructure which is not captured by the I mean by the home source data,
Right.
copper, yeah, radiations. Yeah. So that experiment he can just try.
Right. Yeah. Absolutely.
Yeah. This,
Yeah. Okay. So this is also with the excess titanium. This data is for the excess titanium, and not yet. Mm. Okay. But you already did the series of experiments with the different temperatures. Okay. Great. Very nice. Hmm. Fantastic. Yeah, very nice. Mm-hmm. Yeah. Transport. Yeah. Amazing. So, like, what is the key unknown here is that you don't understand why you don't understand where inflammation is happening. At whatever the peak is coming from. Right? 600. Mhm. Yeah. But I remember the band structure here is it's actually small band gap, zero point 0.4
Yes,
EV
yes, yes.
semiconductor, right?
At least calculated one, because we could not be able to make the experimental one because at the time we didn't have ultra pure samples. Actually, I think Jayanto can now check it with his
Yeah.
99% here.
Yeah.
Uh,
And you should check the optical as well. You do UV to check the. Did you use UV to check? Yeah, I mean, and I think the here, yeah. So the if we need to solve the mystery, what's happening at 616, and because it correlates to the transport. This is the other thing we need to be careful, right? There's definitely a change in the transport, which is not just some precipitates. This is quite significant, right? You guys have seen the data on the transport. Can you go to the next slide? Yeah, look at that, right? 600 something, and just like there's a big change. Hmm. Okay, so it's nothing to do with the actual structure. Anyway, this is not for the phase pure compound, right? You had to do SPS later and compact it and stuff. For the phase pure compound that you made, is it are you able to get a nice block, or do you still have is it still brittle? You need to do SPS to compact it and stuff. Mm. Okay. Okay. Still some steps to go before we get there. Yeah, so if you guys this SPS is done because we had to compact it later to measure thermoelectric properties. This is non-ideal. Ideally, you want to take the sample as is from DJS and cut it. If it's big enough, there's no voids, but then it depends, right? Mhm. Yeah, and the, okay. Okay. I mean, yeah. So the transport data you collected for copper germanium telluride was the one from the experiments in IIT Kharagpur, right? Not from the DGS, or from the DGS sample. Oh,
yeah.
collected.
NTU.
Did you do SPS on that as well? Okay, okay. What was the temperature, pressure? Low pressure. So 300 Celsius. Okay. Six. Yeah, so this is one thing you have to be careful. Remember your problem. I didn't realize that you did SPS because if your porosity is low, your thermal conductivity will be low. So what you see might not be the intrinsic thermal conductivity because you could have porosity, low density that's causing your thermal conductivity to be artificially low. You're not measuring the intrinsic limit. So you have to get 95% or more density before you put it in the transport measurement. It doesn't matter so much for electrical, probably. Okay, especially for CVAC, it doesn't matter. Okay, electrical conductivity may change because your grain sizes might go up if you use a higher temperature for SPS, you get a little bit larger grain sizes. Maybe your conductivity goes up a little bit more. But thermal conductivity should be done on a fully dense sample. Otherwise, it's artificially low. That might be the reason why you're getting this negative value. Okay. It might not be some exotic physics. Just
Yeah, that
hearing.
makes sense.
All right. Mhm. 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 This is old data. This is all old data. Yeah, yeah. But you showed this last time, right? If I remember. But maybe this is not a problem with the pure phase pure sample. We'll find out. Yeah. Then it's nothing intrinsic to the material, right? It's got to do something else. Yeah. So, Partha, for us for this material, right? This is the challenge. Like we can make the material now more or less phase pure, but the phase is already reported by you guys,
Yeah,
and so the transport would be useful. And I think if we can de-dope it, right now, if you look at the values here, the CBAC is quite low. I think
yeah,
it's in the band. So the idea was to try to introduce some silver or things like that on the A side and the copper side, and then
yeah,
maybe causes some de-doping to happen. So I think this is what Jayanta is going to try.
yeah, yeah.
The mobility is not bad, given like Kerry concentration is 10 to about 21. The mobility is actually pretty good.
Mm, mm,
Um, so, but the effective mass is not. I mean, this is a CVAC effective mass, right? That's okay. It's not, no, but I mean, it's the 0.55 ME, right? So but this is averaged over all the density of states. It's not just the inertial effective mass for the lowest band. Ask Pawan this. Okay, is it what is the inertial effect? Like in the mobility calculation, what effective mass to use? CBAC comes using the CBAC effective mass. There's some details that you should check with Pawan. Yeah, but the CBAC. So the M star here is the CBAC effective mass. And the CBAC effective mass takes the whole Fermi surface. Okay, but your inertial effective mass, the conductivity is usually dominant in one of the bands. That's the lowest lying band. That's called the inertial effective mass. You can check that. That comes from only the conductivity. So if you look at the sigma, is NE times mu, and mu is E square tau or M. That M, I don't know if that will not be the same as subjective mass. I'm trying to say. Double check. So you have to. So when you calculate CBAC, there's an approximation of tau that comes out of it. You plug that back, and then you can calculate it. Something like this. Yeah. Okay, so we have phase pure. We have two phase pure compounds. Congratulations.
yeah, it's great. I think Jayanta, as you have made phase pure sample for copper telluride, so I think you use the same method for silver copper telluride. So I think that is going to give you probably the same kind of success actually in your Julietting method because you already have the model for silver for titanium telluride. Yeah. So yeah, so Kedar, probably I will take just couple of minutes to introduce one of another students who probably joined little later. So Ochinto right now is in Hokkaido University. So he just submitted his thesis and he moved as a postdoc over there. But he is the person that who did all these the telluride work actually, telluride, selenite works, and then it is now it is for continued by Ornov actually. So maybe Ochinto, do you have some feedback or suggestion on the telluride compounds? Because I mean, now Jayanta is quite successful in making the phase few samples actually.
Yes, sir. So actually, sir, the question is now with the phase transition pointer. So we have couple of question for the phase transition that we have observed, and there is the other phase transition, some peaks in the DSC curve around 300 degrees centigrade. So that are the two major questions we have to just address. So probably as we have mentioned that the single crystal grow can help, or just I want to ask that if we cannot make the single crystal, or if we can directly use that powder sample for the to check the diffraction pattern, like for the SAD pattern, is it possible? Means probably the low intense peak it is not visible in the powder XRD pattern. So if we take the SAD pattern, can we see the uh,
Kedar, can you please give, I mean, what do you think that?
So it's doing SAED, you mean, right?
Yes, yes,
yeah.
yes. So,
Yeah, we should be able to do it. So Jayanta is preparing, I don't know which samples now because we have two of them, but he is learning how to do this PIPS. The PIPS is a way by which you can make very thin samples for TM. And then we have some nice TM facilities here. And we can probably try to get not just SAED, but both bright field TM, SAED mapping, of course, and maybe even STEM if we're lucky. So I think that would really
Mm,
put an icing on the cake. So we can definitely do that.
yeah.
IWA phase, we don't know.
yeah,
This is what Joyata is trying to
Mhm.
find out.
Mhm.
yeah.
So at this point, I mean, Jayanta like has quite a few things to do.
Yeah, yeah.
Instead of finding out what he prioritizes on, right? Because
Push him, Kedar, push him.
no more holiday for you, Jayata.
Mhm.
Yes, yes, yes. Yeah. Yeah, so I mean, it's very exciting. So I think you can focus on these two, Jayanta, for the next
Yeah,
3 6 months. But now I think he's quite well trained. I mean, like he spent a year and all the equipment is there, and there's people supporting as well. So if you want to do the TM, like Cheng Guang can help do it. I think you saw the EDAX. I think Cheng Guang and there's other students in the team who can help. Yeah, and then the setup is very robust because actually what you don't see here is we have an engineer who spent a lot of time just automating the setup.
all
So
right.
now it's very nice. It's very repeatable. You can, I don't know, Jayanta helped in contributing to that as well. So I think it's quite robust. It's almost like a programmable furnace, but with direct joule heating.
Yeah. So, what do you think that what would be the cost of this setup? Just minimum.
No, nothing. Like there's a tube furnace, there's a high voltage power supply, there's a
That's all. Do
that's it.
you? Yeah. Okay. Okay.
I'm
Okay.
not kidding. Like I think the more people who use it, the
Or
better it
no,
is.
we can just do
Amazing.
it in our lab. So,
Yeah. Please, I'm not even exaggerating. Like Jayanta, you can if you have maybe not this time, but maybe
yeah,
sometime in the near future,
yeah,
or you can send Arnab here or something, and you can pick it up and
yeah,
take a
yeah.
list of the parts, and you just please go ahead and make it.
Great. Yeah. Thank you.
Oh, of course, of course. I think this is the whole idea, right? And then, like, if we combine this materials by design, we want to go to a like property directed design. The more people use it, the better. We learn all the problems with the setup.
Yes.
So
Yes.
I think
Yes.
it'll be very good to do it.
Yeah. No,
So
it's really nice. Yeah.
I had an unusual question for you. So this is one to consider. I mean, no pressure either way. So we sent this paper, the silver antimony telluride paper, to Nature. Okay, and the main editor looked at it for about 2 weeks. So she came back to me and she said rejected. But she actually liked I shouldn't say liked. She read the whole paper. So it wasn't like a standard desk reject. So I wrote back. I was like, you cannot say this is flash tube heating. It's not. It's very different from that. We're doing solid state synthesis. And I said that, we are actually able to synthesize phase pure compound. I wrote to her, say, we have synthesized a copper titanium telluride, which is greater than 85% phase purity, because I didn't know that it's 99%.
Okay. Yeah.
So there's a possibility, if you're okay with this, where we can fold some of your. We don't have to do the full characterization. We can maybe just show that we have synthesized a previously unexisting phase with DJS and add it to the current paper. And of course, all of you can be involved in the paper if that's something you're interested in. Because right now it's focused on thermoelectrics, but we can say something like, this is to make, inorganic functional materials for different properties. So again, but I don't want to take away from the whole body of work that you have done. So
Yeah, yeah, yeah.
it's just for you to consider.
Yeah.
What I will just present it to her anyway, if that's okay. And I will mention that this is in collaboration with you guys, and we're thinking of writing a separate paper, etc.
Yeah.
And let me see what she says. I'll give you the feedback, and then it's for you to decide. No pressure either.
Yeah, 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 absolutely. Yeah. So yeah, I think you can. I mean, telluride compound is 99%. So definitely you can present that. Yeah. So
Yeah,
if
I
you
will just present it. And I will not say either way that, this is good. I will just mention that this is done. Let me get her feedback. She says, well, if you can add this to the paper, then yeah, we will send it out for review. Then I will tell you this. And then
yeah,
you can decide if you want to include some part of it or do you want to, because, like the way the nature thing works is also, we show that it's there, but the full paper can be a separate chemistry of materials or JAX, which is what we can work towards. And this can be a nice parallel paper that we can, because it takes forever for nature. There's no guarantee.
yeah, 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 yeah. So it's a mother nature, right? Yeah.
Yeah, it's Mother Nature.
it's, it's yeah, you have to push.
Matrabhumi.
You have to
Try
push.
and see. So I will talk to her tomorrow actually. So if that's okay, I'll ask Jayanta to prepare one slide on copper titanium telluride and one on copper germanium telluride, and just show her that we have these results. And after her feedback, I will get
Yeah,
back to you,
yeah,
and you can decide whether it makes sense or not.
yeah.
Again, it's just
But yeah, just one point. Just copper germanium telluride is a brand new compound,
yeah,
and just you have to be careful
yeah.
because it's this selenite telluride community is very competitive, and I think and that is why actually I call this meeting, because
Um,
probably this compound we want to finish it by maybe month if possible, actually. Yeah.
okay, okay,
Yeah. So but copper titanium telluride, I think it's okay, because at least
the
we
structure
have
is solved. Yeah,
yeah, structure is known to the community. Nobody so far could be able to make the phase view sample. So yeah,
okay,
so this is just the comment from our side. So
sure,
copper titanium telluride, no worries.
okay,
And but this one is a brand new compound. I think both of we should uh, publish together first.
let's do
Uh,
that.
yeah, yeah. So
No, that's perfect. So now I know. So I will present the copper titanium telluride stuff. I
yeah,
won't present the germanium telluride, and
yeah.
then we'll see what
Yeah,
that.
because germanium compound, we both will publish,
Yes,
but for the first time to the community, it's, yeah,
yes,
yeah,
perfect.
yeah,
Understood. Great. Sounds
yeah,
good. So I think that's clear. I think Jayanta, you have a month
yeah,
for
yeah, yeah.
the
No,
germanium telluride
yeah.
stuff.
It would be great, Kedar, if we could at least publish this germanium compound
Yeah,
as soon as possible, because this field is very competitive. So, and large number of people are working in this
okay.
selenite compound. If somehow somebody can get,
You get scooped.
yeah, then it would be, you
So
cannot be the first one. Yeah.
yeah, so can we so what is the key few things that we need, right? So Jayanta, you can even ask Cheng Guang to do the pips for you, right? If you're not confident, that's also okay. But you need to have a minimum list of things that you absolutely need for the copper germanium telluride for it to be published.
Yeah.
So what is that list? Maybe we can decide that.
So the plan is just we will report the phase. I mean, new phase that characterization by single crystal XRD, as well as the radial refinement, and also the very interesting thing what you have done, that is the phase purity, and then mainly that phase pure synthesis itself is a very good.
Done. So we don't
Mistake.
need anything else for that paper. Is that right?
I think we can just add the characterization technique. I mean, that what probably people are doing, but that is not the key for this. We don't want to show that it's ultra low or very low, but we want to show that this is a new compound. I mean, the first time report, the structure first time report, and this is the technique by which we could be able to solve the. I mean,
I
the
think
purity.
that's
Yeah,
great. So I think
yeah,
it seems like we have all the data for it. So I'm happy to spend time on this, writing it up. It seems like you
yes,
also have a draft. So,
yeah,
well,
yeah.
at the point you're ready to share, please share. I mean, Jayanta can help
Absolutely,
write as well.
absolutely, yeah. So I mean, we will do it
Okay.
among ourselves. So it's not a big deal.
Okay.
And Arnab is just, I said Arnab that I pushed him that you just finish it. Otherwise, you will be
Yeah.
in pain that if somebody
That's absolutely true. That's the worst
publishes
kind of
it.
pain you can feel. You know, you'll be telling your grandkids about this pain.
Yeah, because for us it's fine because we have faced this problem in our life actually. But
Yeah.
for them, that they will be really
I
shocked.
already have battle scars from stuff that I should have published that someone's don't want that. Well, I agree.
Yeah.
Okay, so very clear. I think it's very, very good. We'll prioritize this. We can
Yes.
even wait on the copper titanium if there's anything else required.
Yeah.
I think one thing we can do is while we send it out for review, Jayanta, let's try to get the TM right, and then if for the germanium right, then whenever the reviews go, whatever, we can also supplement that data further with TM. Then let's just do that.
Yeah. 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 So I think Arnav will finish the first draft and will share with all of you, and maybe then after that we can just start working on it, and let's finish it by a month if possible.
Sounds good.
Yeah. Okay. Okay. Yeah.
Prioritize it. But anyway, it's all like icing on the cake. At
Yeah.
the end of the day, we just report the structure. That's the key idea.
Yeah.
Great.
I mean, if this kind of is okay, it's okay for you. This is the way it go. Yeah. Yeah.
It's your work, so I'm happy to follow you.
Oh, no, it's okay because it's collaborative work. So I'm really happy the way you are helping us as well. Yeah.
Not at all. It's really fun. We'll be learning a lot. Okay, I have to go for another meeting in 1 minute. But it's
All
good.
right. Yeah. Okay, Kedar. Yeah. Thank you once again. That we will maybe once in a month or we
Yeah.
will meet and then we can just get update from our such that we can push our students to.
Sounds good. Perfect.
All right.
Yeah, in
Yeah.
a month, so we have a plan. We'll have a draft of the paper almost finalized, ready to submit, and
Yeah.
we'll have some more progress on the measurements Jayanta is going to do in his holiday
Yeah.
when he comes to Kharagpur, and then we get
Yeah.
some numbers.
Yeah.
So maybe
Yeah.
Jayanta just write down a few things, right, for what is planned for next month, so then we can start from there.
Yeah.
Every month when we meet. Okay,
Yeah. All right. Yeah.
great. Thank
Okay.
you.
Thank you once again, Kedar. So have a nice time. And probably if you, what I said each and every time, if you come to India, just plan for a day or two. So for our institute.
I want to come, but it happens soon.
Okay. Yeah.
Okay.
All right. Yeah. Okay. Bye. Take care. Yes. Huh. Depending on that. Yeah. Exactly. So all the measurement. Yeah, I think that is the plan is but তুমি যদি তোমার কত হয়েছিল ওই যেটা ওই প্যালেটের তোমার ডেন্সিটি কিরকম ছিল okay so even if you probably improve 95% the property is not going to change much actually তুমি আবার অর্ণবের সঙ্গে ডিসকাস করে নাও ওটা নিয়ে যে and then I think finish the paper because I always told Arnav because compound একবার পাবলিশ হয়ে গেলে then I think you're safe you can do the follow up work but because there are a lot of Chinese people are just chasing this I can see actually in these compounds so okay so I think
স্যার
Arnav
ওই অচিন্ত আছে, তো আমি তো জিজ্ঞাসা করতে চাই ওই যে জয়ন্ত যে সিরিজ করেছে কপার পর টাইটানিয়াম টেলুরিয়াম,
mhm.
তো ওটাকে অচিন্ত আমি যদি 50 ডিগ্রি সেন্টিগ্রেড বা 60 ডিগ্রি সেন্টিগ্রেডে হিট করি ফর 7 days or 20 days, তাহলে কি ওই রম্বয়েডাল ফেসটা জেনারেট করতে পারে?
50 ডিগ্রিতে
ওই ফেস ট্রানজিশনটা হয়েছিল রম্বয়েডাল থেকে কিউবিকে, ওটা অ্যারাউন্ড 50 ডিগ্রি সেন্টিগ্রেডের দিকে হয়েছিল। তাহলে আর একটা স্টাডি দেখতে পাওয়া যায় যে যদি 50 ডিগ্রি সেন্টিগ্রেডে হিট করা হয় 20 days জন্য।
আচ্ছা, হ্যাঁ ওটা করে দেখা যেতে পারে, কারণ ওটা কেন আসছে না সেটা একটু মানে ওটাকে আমাদেরকে অ্যাড্রেস যদি করা যায় কোনোভাবে, যদিও বা
কারণ ওটা
হচ্ছে না
হয়তো
সেটা কেন হচ্ছে না।
জুল হিটিং এ ওটা হয়তো কিউবিক ফেসটা স্টেবিলাইজ হয়ে যাচ্ছে, বা
হুম
রম্বয়ের
হুম
ফেসটা ওটা পাওয়া যাচ্ছে না, তাই জন্য ডিএসসি
হ্যাঁ
সিগনেচারে ওটা দেখা যাচ্ছে না।
হ্যাঁ হ্যাঁ, তো সেটা যদি ওটা কেন হচ্ছে না, কিভাবে অ্যারেস্ট হচ্ছে, যদি কিউবিক ফেজটা অ্যারেস্ট হয়ে যাচ্ছে তাহলে ওটা কিভাবে হচ্ছে সেটা একটা এক্সপ্লেন করতে পারলে সেটাও ভালো হবে, না হয়তো
তাহলে ওটা
এক্সআরটিতে।
কতটাই হিট করবো, 50 ডিগ্রি সেন্টিগ্রেড ওর হায়ার টেম্পারেচার, তো
হায়ার
ট্রানজিশনটা হয়েছিল।
তো আমরা, 50 50 100-র কাছাকাছি হিট করে আবার দেখা যাক কিছুদিন ধরে, যদি আর তারপরে যদি সিঙ্গেল ক্রিস্টাল যদি গ্রো করা যায় ওখান থেকে।
সিঙ্গেল
যে
ক্রিস্টাল গোল করতে একটু স্যাম্পেলটা কি মেল করতে হবে, না আমি 400 500-তে হিট করে পাবো, নাকি 900-তে তুলতে হবে,
উম,
যেরকম তুমি করেছিল?
ওটা আর একটা মানে অপটিমাইজেশনের ব্যাপার চলে আসবে, কারণ ওটা জানেনি যে হাই টেম্পারেচারে আবার গেলে কি হবে স্যাম্পেলটা, কারণ অলরেডি 450-তে। হ্যাঁ হ্যাঁ হ্যাঁ, তো সেক্ষেত্রে একটু ডিফিকাল্টি হয়ে যাবে। আর আমরা যদি অ্যাজ ইট ইজ স্যাম্পেলটাকে ইউজ করতে পারি সেটা সব থেকে বেটার হবে। ওই যদি এসএইডিটা করা যায়, সেখানে যদি কিছু সুপারস্ট্রাকচার রিফ্লেকশন দেখতে পাওয়া যায়।
আর কিন্তু ডিএসসি হিট ক্যাপাসিটি তো কিছুতে দেখা যাচ্ছে না, তাহলে হতে পারে যে
হুম
কম্পাউন্ডটা কিউবিকেই স্টেবিলাইজ হয়ে গেছে।
হ্যাঁ
অ্যাটলিস্ট তো সিগনেচার দেখা উচিত হিট ক্যাপাসিটি।
হুম, বাট কোনোটা লো টেম্পারেচারে তো কোনোভাবেই ট্রানজিশন দেখা যাচ্ছে না, যদি কিউবিকটা তো ডিসঅর্ডার, তো ডিসঅর্ডার স্টেটটা যদি ফ্রিজও হয়ে যায়, আমরা তো টেম্পারেচার যখন কমাবো সেক্ষেত্রে তো দেখতে পাওয়ার কথা, কারণ হাই টেম্পারেচার ফেজটা তো অটোমেটিক মানে আমাদের অ্যাকচুয়ালি অর্ডারিং হচ্ছে।
তাহলে ওই 100 ডিগ্রিতে লং টার্ম হিটিং করে দেখা যেতে পারে যে কোন সিগনেচার আসছে নাকি হিট ক্যাপাসিটিতে বা
হুম
ডিএসসি।
হুম হুম হ্যাঁ
তুমি অচিন্ত, তুমি কি তোমার অচিন্ত,
হ্যাঁ স্যার।
তুমি সিনথেসাইজ স্যাম্পল নিয়ে তোমাদের তো রেগুলার সিঙ্ক্রোটনে যাও,
হ্যাঁ হ্যাঁ
তুমি অ্যাটলিস্ট হোম সোর্সে আর দেখতে পাবো না। তুমি
হুম
যদি
হুম হুম
মনে করো তাহলে তুমি একটা ওই একটা স্যাম্পল, একটা সামান্য স্যাম্পল নিয়ে তুমি সিঙ্ক্রোটনে ওই টেম্পারেচার মেজারমেন্ট করে দেখো যে তোমার অ্যাক্সেস আছে, যদি তুমি
হ্যাঁ
দেখতে পাও।
ঠিক আছে, তাহলে আমি এবার আহ, কথা বলে নেবো
ওটা তুমি করতে
প্রফেসরের সাথে।
হবে, তোমাকে লো টেম্পারেচারে যেতে হবে, যেখানে তোমার ওই পিকটা প্রমিনেন্ট হবে।
আচ্ছা, টেম্পারেচার ভেরিয়েবল।
টেম্পারেচার ভেরিয়েবল হাই টেম্পারেচার না, হাই টেম্পারেচারে তোমার তো মনে আছে যে যদিও ওটা তোমার ফেসাইজেশন হয়ে গেছে
হুম হুম
রুম টেম্পারেচারে, বাট ওই পিকগুলো কিন্তু খুব ফেডেড পিক ছিল।
হ্যাঁ হ্যাঁ
তো সেটা তুমি ওই ওই রুম টেম্পারেচারে পাউডার নিলে বা হাইয়ে গেলে পাবে না, তোমাকে নিচের দিকে যেতে হবে।
হুম হুম
তো
ওকে।
অ্যাটলিস্ট তুমি যদি এ পর্যন্ত যেতে পারো, জাস্ট লিকুইড হাইড্রোজেন টেম্পারেচার, আই থিংক পসিবল, তোমার জানাই বোধহয়।
আচ্ছা ঠিক আছে, আমি তাহলে ওটা একটা কথা বলে নেবো।
একটা বা দুটো স্যাম্পল যদি নিয়ে দেখতে পারো, ওখানে তোমার লেখার কিছু নেই, তোমাদের অলরেডি তো থাকে প্রত্যেক বোধহয় 3-4 মাস অন্তর অন্তর।
হ্যাঁ হ্যাঁ, কারণ এই মাসে একটা আছে, তারপরে বলছিল নাকি সেই এখন লেট হবে অক্টোবরের দিকে মনে হয়।
আচ্ছা,
তো এই মাসের শেষের দিকে একটা আছে স্লট।
দেখো জয়ন্ত যদি এই মাসের শেষে কি হবে পসিবল না, বাট আই থিংক ডিফিকাল্ট হয়ে যাবে নাকি। আর তোমার কাছে স্যাম্পলে 99% স্যাম্পল যদি থেকে থাকে একটু দিয়ে দিলেই হবে, বেশি তো লাগবে না।
হ্যাঁ, বেশি লাগবে না।
তুমি একবার তাহলে একবার অচিন্ত তোমার স্যারের সঙ্গে তাহলে না কথা বলে নাও, যদি ওটা নিয়ে যাওয়া যাবে কিনা।
হ্যাঁ হ্যাঁ, ঠিক আছে, আমি তাহলে কথা বলে নেবো এই মাসে শেষের দিকে আছে 26-27 করে। হ্যাঁ, তো আমি একবার তাহলে কথা বলে নেবো, তারপর আমি স্যারকে তাহলে জানাবো। তো ঠিক আছে। হ্যাঁ, শোনাচ্ছি। কাকে বলছিস? ও আচ্ছা।
ওটা বরং লিখে দেবো কিছু একটা হচ্ছে বলে, পরে যখন স্যার ওই ভ্যারিয়েবল টেম্পারেচার এক্সিটি করবে ওই জায়গায়, সরি সিঙ্গেল ক্রিস্টাল করবে, তখন আমরা ওই টেম্পারেচার মেজার করি। দেখা যাচ্ছে স্যারের সাথে কথা বলে নেবো তারপর কিভাবে ডিল করবে। হ্যাঁ হ্যাঁ, যেমন শ্রীদাস স্যার বললো। আর ওই হিট ক্যাপাসিটিটা ওটা তো স্যাম্পল দেওয়া আছে, ওইগুলো এসে যাবে। আচ্ছা, ওকে অচিন্ত অল গুড, অচিন্ত সব ঠিক
হ্যাঁ,
আছে।
হ্যাঁ, হ্যাঁ, ঠিক আছে সব। হুম, হুম। এদিকে সব ঠিক আছে তো?
হ্যাঁ,
আচ্ছা, আচ্ছা।
ঠান্ডা কমে গেছে ওখানে, বরফ তো
হ্যাঁ, হ্যাঁ,
কমেছে।
এখন এখন গরম, মানে হালকা হালকা গরম আছে, খুব বেশি না।
এখানে হালকা হালকা ঠান্ডাও নেই।
না, ঠান্ডা নেই। ঠান্ডা বৃষ্টি হচ্ছে মাঝে মধ্যে, তখন একটু ঠান্ডা ঠান্ডা। আচ্ছা, আচ্ছা, না এখানে অতটাও গরম নেই, সোয়েটার পরতে হয় সন্ধ্যার দিকে। হ্যাঁ,
তাহলে ঠিক
ঠিক
আছে।
আছে। হ্যাঁ।
ঠিক আছে, জানি তাহলে পরে ফোনে কথা বলবো তোর সাথে।
হুম, ঠিক।